Good evening, I'm Mike Knetter, and welcome to the UW Now Livestream series, where we bring you experts from our community to talk about timely and important topics. From record-breaking temperatures in the Pacific Northwest to tropical storm Elsa in the Northeast, weather is a hot topic this summer. But what's happening with weather patterns in other seasons? And what do we know about the causes and consequences of long-term trends in weather and climate? What are the impacts on soil erosion, sea levels, and coastal flooding? Can we mitigate or must we adapt to these changes? Joining us to discuss these topics and more is Professor of Atmospheric and Oceanic Studies, Jonathan Martin. Jonathan, it's great to have you here with me in one alumni place. It's the first time we've done a show in this series where I've been able to be together with my guests. So we are excited to do this, and what a great person to have on the show. John is an old friend, and we in fact frequent the same coffee shop in Madison. So we don't have coffee tonight, and I'll explain that in just a minute as well. John earned his PhD in atmospheric science at the University of Washington and is a nationally known expert on mid-latitude weather systems, such as snowstorms and severe thunderstorms, and how those systems interact with the climate system. He's authored or co-authored more than 70 scientific publications, including the leading undergraduate textbook on atmospheric dynamics, Mid-Latitude Atmospheric Dynamics, a first course. In March, he released Reginald Sutcliffe and the Invention of Modern Weather Systems Science, which is a biography that highlights Sutcliffe's contributions to modern-day weather forecasting. Professor Martin is a recipient of the Underkofler Excellence in Teaching Award, the College of Letters and Science Mark Ingram Distinguished Faculty Award, and the Hamill Faculty Fellow Award. I would just like to point out the Hamill family is our official sponsor of this evening's segment, since they supported Professor Martin's research and my bad habits. Locally, John is one half of the Weather Guys with Vice Chancellor Steve Ackerman, where they appear in the Wisconsin State Journal and on Wisconsin Public Radio. John, it is great to have you here in person, and I can't wait to hear your thoughts about what we're seeing in weather this summer and in other seasons and how that relates to climate.
Well, thanks, Mike. It's a great pleasure to be here, and to be able to do a sort of a show like this with you is even a better thing than just having any opportunity that comes along. It's fantastic to be able to do it with a friend. And we have had some exciting weather, I think, not just in this summer, but in other seasons. And it's always exciting to talk about it. So I'm very happy to be here.
Great. Well, I'm going to give you the floor, and I'm sure our audience is going to be interested in what you have to say. And they'll be throwing some questions my way, and we'll take those up when we're done. And it'll be just like the Weather Guys, except you're without Steve tonight.
Great. That's great. And there's some advantages to that, because we're both speaking English, not that Long Island dialect, which only marginally compares to English. So
there we go.
No, Steve, you know I'm kidding. You're a great guy. And we never have trouble communicating. We had an amazing event in late June in the Pacific Northwest. Utterly amazing. And there's been a whole bunch of discussion since that happened. It's only been 2 weeks since. Among dynamic meteorologists around the country, we have, like most groups have, some sort of listserv that you can get on the internet. You can talk about these kinds of issues and so on. Weeks. And I think it's an interesting story, that the notion that, a lot of the media has jumped immediately to suggest it couldn't have happened to the extreme that it did without climate change. And there's plenty of room to have a really good discussion about that for that particular issue, that event, I should say. But I just want to give you a couple of highlights of the event itself. I went to graduate school in Seattle, as you pointed out, and Seattle had 3 days in a row over 100 degrees in June 27th, 28th, and 29th. I was in Seattle on the first day ever when it was 100 degrees. That was July 20th, 1994, and that was a week or so before we left town to come to Madison. So I've been here ever since. And then it happened again in 2009, I think twice. And so prior to the end of June, there were only 3 days in Seattle's history, scattered over a number of years, where the temperature had risen to 100 degrees or above, and then they had 3 in a row. And on the last 2 of those 3, it was 104 and 108, both days set the all-time high on successive days. Further to the south, in the in the east and west of the Cascades, Portland, Oregon had 3 straight days where they set their all-time maximum high. They were 108, 112, and 116 on successive days, each day beating the one before it. And then in Canada, in parts of British Columbia, I think the town was Linton, but anyway, in British Columbia, 3 straight days, a Canadian all-time national high temperature record was set, which never happens. This kind of thing never happens that you set such records on 3 straight days. So I want to show a little bit about what might have been the circumstances that led to that. So if we could have the first slide, Chris. And this is just a picture of the streamlines of the flow at about 3 miles or so above sea level. So the green lines, you might see little hints of arrows on them, indicate the direction of the flow that is over the Pacific Northwest. This was near the end of that heat wave. This was 7 a.m., well, not 7 a.m., 5 a.m. Pacific time on the 29th of June this last month. And the next slide, Chris, will highlight a little shaded area that I put on the next slide, which is what was called in the press the heat dome. There's no such thing as a heat dome. I don't really like that term. What that shading is indicating is a region of really strongly anticyclonically curved flow. And that is, and we can put the next slide on, Chris, that shows flow that's moving clockwise. And in this case, around a really tight oval. And you don't have, most of you probably don't have enough experience with these weather maps. I've had 30 plus years of it. That's a really extraordinary anticyclone that was occurring over the Pacific Northwest. And in fact, as I said, it was about a day past the maximum in the heating of that day. And then just to the west of that, off the coast, the next slide will show a region where the streamlines indicate counterclockwise flow, and that's the red arrow. And that is a region of low pressure at about 3 miles or so above the ground. And in between the two, that's where Seattle and Portland was. And downstream, or to the east of both of those disturbances, the next slide, Chris, would help. Downstream of the anticyclone, at upper levels, 3 miles above the ground, if we can see the next slide, there's a region of high pressure at the surface, indicated by a big H. And then the next slide, I think, shows the low pressure region, which is downstream of the upper level trough, which is in red. And what happens, given that situation, is the pressure is very much higher inland in the Pacific Northwest than it is right offshore. And then the next slide, I think, draws the Cascade Mountain Range in there as a schematic. And you can kind of see that if you have high pressure on the interior of the continent and lower pressure out to sea near the ground, you're going to have flow over and through the mountain gaps. And when it moves over the mountains and through those gaps, it sinks. Air will sink just as water moving over a stone in a stream will have a sort of a subsidence side on the downstream side of the rock. And when the air sinks, it gets compressed, just like your bike tire or a tennis ball if you smash it around on a summer day. It feels warmer at the end of the day because when you compress the air, it warms up. And so the next slide shows just a schematic of some of the flow that was coming off of the higher terrain to the east, through the gaps and over the hills in the Cascades, and flooding Western Washington and Western British Columbia with strongly subsident and warmed air. So very, very bone dry, but really hot air. So here's what I say about this event. I think I probably have the consensus view, or at least a pretty decent approximation of the consensus view. This set of circumstances is extreme, and it may or may not be related to some sort of systematic change in the climate. But it strikes me, and I think a lot of my colleagues around the country, that the extreme temperatures that occurred in the Pacific Northwest, both in Canada and the United States, were probably, the ball was carried down the field by the individual weather system that I've just described to you, more than it was by the climate system. And so there'll be people who will say, oh, that's a sigh of relief. That means that we don't expect these kinds of phenomena to happen too frequently. That may or may not be right, because we're trying our best, really just 2 weeks after the event, to kind of make a reasonable statement about what we think might have been driving the extraordinary weather that was recently visited to the Northwest. And the climate has warmed by about 2 degrees Fahrenheit globally in the last 100 or so years. And certainly, if you raise the average temperature, you're going to have a likelihood of some of these extremely high local temperatures, and that's going to be exacerbated. The likelihood's going to go up. But I don't think the climate system drove this particular event all the way to the finish line. I think it was a combination of the background warming. The climatology of this part of the world at this time of year is for the development of such anticyclones over the high terrain of British Columbia, Alberta, and the northern Rockies in the US. And then the extraordinary nature of this particular set of circumstances forcing the strong subsidence into the Puget Sound and the Portland area, and really driving the temperatures through the roof. So that's, I think, one way to look at this heat wave. It could well have some connection to the climate system, but it's not very obvious to us how it might be connected a couple of weeks downstream. I would say the weather has carried the ball on this one. But it's interesting that we can talk about other seasons in the year as well. And one of the things that I grew up in New England, and so I had a morning paper as a boy, so I loved being out in the snow. And so cold and snowy winters are a very attractive thing for me. And we could talk a little bit later about the wintertime and what we're seeing in the wintertime long-term averages, if that's the way we want to go. You keep going if you want.
Sure. Why don't you say a few things about winter weather,
Okay.
John, and then we'll go to some audience questions. I have a few coming in right now.
Great.
So.
Okay. So as Mike and I were talking before the show, I think people get understandably excited when there's an extreme high temperature situation that develops during the summertime, and they think, oh, well, this is probably some global climate change, at least lurking in the background. But most people don't consider what's going on in the wintertime as a symptom of climate warming. And I've stumbled into this almost by accident because of my interest in winter storms. And so I want to show you a few slides that talk about that recent research. We had a really boring winter here in Madison. That boring for me means too warm and not snowy enough in 2010, 2011, and 12. And here we're looking at a map of the Northern Hemisphere. What I shaded in light blue is a region where the temperature is below -5 degrees Celsius at about a mile above sea level. So that's 23 Fahrenheit. So it's below freezing. And the blue line on the edge of the shading is the boundary at which the temperature is exactly -5 degrees C. And that number didn't come to me out of nowhere. That's really usually a pretty good indication of if you're north of that and colder, you're going to get snow if it's precipitating in your area in the winter. If you're south of that and warmer, you're probably going to have a mix of rain and snow, maybe all rain. And these are all things that I pay attention to. So I had this waiting. And it occurred to me, though, looking at this map, in an otherwise boring winter, I had no prospects for anything exciting. I should say that this was a very cold winter in Alaska. There was snow in Tripoli, Libya. There was snow in Rome, but there was no snow in Madison. And that, of course, frustrated the heck out of me. So I thought I have to do something to preoccupy my time instead of being frustrated about the winter. I thought to myself, there's an aerial extent of this -5 degree air at 1 mile above sea level. I wonder what it does throughout the whole winter, what it does throughout the whole year. And so I started to calculate this area in the light shading. We can go to the next slide. In the next slide, I put July 1st right in the middle of that slide. We can go to the next slide. And so it's a beautiful sinusoid. This is how the top line is the -5 degree. I have 4 other thresholds. We'll concentrate on the top line, which is -5. And the aerial extent peaks around right now, July 10th, 12th. It's minimum at July 10th and 12th, and it peaks in late January. So I said it wrong. I put January in the middle of the slide. So every one of the temperature thresholds at that 1 mile above sea level that I chose have exactly similar shapes over like a 65-year average. But year to year, they may be quite different. So we can go to the next slide. We have some fun with this. The top line here represents a 72-year time series that goes all the way back to 1948. And every one of the dots on that top line indicates an average of 90 days from December 1st to February 28th of each of those winter seasons from 1948-49 all the way to last one, 2020-21. And you can see what's happened over this 72 years is that the average aerial extent of that cold air, that is averaged over every day of the wintertime, December, January, February, it's systematically shrinking. So even when you go to the wintertime and you look at a really seemingly obscure measure of is the hemisphere colder or warmer than it used to be, it is not only unequivocally warmer, but systematically getting warmer over the 72-year period. And there's 3 different colors you might see on that top line. That's 3 different data sets that try to use the same original data, but then they manicure it and they process it in slightly different ways. So it's a very robust signal. Each one of those different data sets has the exact same trend. And that trend is about a decrease of about 4.5% aerial extent since the beginning of this time series. So if we can go to the next slide, this means that the hemisphere is not able to get as cold anymore as it used to. And you don't have to just look at a seasonal average over the 90 days. One can look at individual daily time series. I'm showing you the two extreme winters from the entire time series. 1971-72 is the red line. Back behind it with the blue thin lines are the maximum values for any calendar day and the minimum in the entire 72-year time series. Then the blue line in the middle is the average for each calendar day, and then it's straddled with some gray, and that's the plus and minus 1 standard deviation from that average. And then 2013-14 is the green line. And I've highlighted on both of those time series individual instances where on the 71-72, that's about the time when President Nixon was in China, in fact, the hemisphere was 2 standard deviations greater in aerial extent than normal for February 1st and 2nd of 72. And then in 2013-14, we're more than 2 standard deviations below the normal just before the beginning of January in that year. So I decided to call those 2 standard deviations bigger than the average. Those are going to be called extreme cold days, and 2 standard deviations below the average, if it happens on a given day, are called extreme warm days. If we can go to the next slide, Chris, this is really unbelievable. This is, you can't read it all, and I'm sorry that you can't, but you can see that it's kind of front-loaded. On the left-hand side are all of the days that qualify as cold events, extreme cold days, and on the right-hand side in red are all of the days that qualify as extreme warm days. And this is a time series that goes all the way through, unfortunately, only 2013-14. But there are 117 extreme cold days in the time series up to that point, and there were 187 days on the extreme warm side. And as it turns out, if we can go to the next slide, you'll notice something interesting. So I'm going to give you a few conclusions about the wintertime. Over the last 72 years, the cold season cold pool, -5 degrees at a mile above sea level, has decreased by 4.6%. Systematically done so. Amazing. The next point is the shrinking cold pool is directly a result of greenhouse warming. You can't create or destroy cold air except by radiation in this instance, and the radiation is being changed by changes in the chemical composition of the atmosphere. Here's the most interesting thing on All-Star Night. Extreme cold days have stopped happening. The score, if you keep score of how many extreme warm days we've had since the last extreme cold day, it's 197 to nothing since February of 94. The last cold day, by that definition, occurred a week after I interviewed for this great job that I have here at Wisconsin. So that's an incredibly long time, believe me. The score is 197 to nothing, warm days to cold days. It just doesn't get cold anymore. The game's up on that. And then I don't think there's anything else. Let's see if there's one more slide. I guess there's none. So that's how the wintertime can be diagnosed as changing.
Now, John, you stopped that data analysis in 2013-14, is that correct?
I haven't continued updating that slide,
Because
but I have the analysis.
Have we not had some extreme cold days since then? No polar vortex?
No,
Cold?
and it's hemispheric now.
Okay.
Keep in mind, it's the whole hemisphere.
Okay.
But, yeah, so we've had cold days, but the hemisphere has not had an exceptionally large extent of that cold air since 1993.
It was so cold in Rhinelander this winter, I had to get the striker ice, hard water,
Yeah.
bibs, and jacket for ice fishing.
And that's a great example of the difference between weather, and that's local,
Right.
and climate. And the climate is occurring on such a grand scale, but yet you can measure aspects of that grand scale and come to these conclusions, which are quite striking. So we have a warming planet, there's no doubt about it.
So an interesting question just about how we talk about these things came in from Jim Kennedy, and I'm going to throw that out first. So how much of the interest in these events is based on sensationalizing terminology like polar vortex and heat domes, and is that kind of hyping this, and people begin, we're all aware that the Weather Channel, they need eyeballs too.
Yeah.
So maybe they're kind of scaring us about the weather. It seems like we get, people often talk about the snowpocalypse that we never have. They're forecasting a huge winter storm, get 2 inches. Is there a bit of sensationalism going on in the media with this that makes it harder for the science to really break through by creating a little skepticism, maybe?
I think it promotes, I think this is a great question. So thanks for that excellent question, Jim. I think that I'll call it, there's 2 different things that go on at the same time, I think. There is a media description of the weather and climate, and then there's a bus stop description. I'll call it the bus stop description of the weather and climate. And the bus stop description of the weather and climate underlies the media one. Because if there weren't general interest at the bus stop in the weather and climate, and there is, then there wouldn't be any incentive for the media to sensationalize it. So I think that builds upon a general, broadly held and inherent interest in the weather and climate. Most people have. But it is a problem for trying to explain something in a more clinical and a more sober way as a scientist when you're competing against a media that really has to compete to try and get people to pay attention to what they're saying. And so any chance I get, like when we're on Larry Mueller as the weather guys, or get a chance to write in the newspaper, and we may get syndicated this year, that's kind of exciting. We tried to tamp that down, the sensational side down, but then amplify the scientific side. And I think if a person's really interested in the weather and climate, they will come along, just as I did as an undergrad, they come along to realize that the actual real description of things and the clinically accurate one is even more interesting than the sensational, as it turns out. So I stand very happy to try and beat that stuff down, because I know I can't lose. I know I've got a winning hand. The interest in the weather and climate is pervasive and only deepens when people learn more.
Well, I believe that. And I also think that on different sides of this discussion, we have people that have, let's say, different natural interests in what the actual outcome is.
Right.
So depending on where I live or where I own my land, depending on what my occupation is and what regulation might do to my industry, I might have a desire to have a certain perspective on what's going on with climate. By the same token, some people would say, does the research community have an interest in maybe alarming us about this, because then there's more funding for research because we have to stop this enormous problem? So could you comment on, it seems like there might be reasons on many sides for people to have maybe not perfect alignment with truth. And I have some of my own thoughts about that, but what's your perspective on that?
That's a really good question. I think that there is a tendency for just about any human being to project his or her interests onto an issue of the day. There's almost no way to avoid that. From the business side, you may not have a compelling pushback like we do in peer review in science. So if I really do try to project, let's say, my interest in winter storms, and I say that everything that happens this winter is a function of understanding these winter storms, and I send that in as sort of the premise of a proposal to the National Science Foundation, which will be reviewed blindly by colleagues, I don't know who's reviewing it. They'll say, come on, John, that's ridiculous. There's so many other elements of the weather that will conspire to produce what you're going to experience in Madison this winter. It won't just be your favorite winter storms. So I can't get away with that in the face of peer review. Similarly, if I try to lace my proposals that are more serious with climate change, climate urgency, and all the rest of it, people who are reviewing it see right through it. If you don't have an argument to make that's based upon solid physical premises and observations and in theory, you can't get away with that. So I think there may be a tendency among people who feel themselves wanting to project their own interests on the weather and say, let's say I own a condo in Florida. I don't want the sea level to rise. I'm going to say anytime I hear that the sea level is rising, it's nonsense. That's clearly a projection of your own interest. If I write that in a proposal and I say the sea level is not rising, I'm going to get hammered because people are going to say, no, we know that this is happening, and you're disregarding that. And as blind peer review, I can't get that proposal funded. So if there is more funding and the government decides to take a role in fertilizing the scientific community to learn more about these urgent problems, and even if they are only perceived to be urgent today, and 20 years from now they're not seen to be urgent, we'll still go through a phase where we learn more about the problem. But you won't get your hands in that money pot unless you make a serious, sober, scientific proposal to your community. Because science is not different from any other human activity in the sense that we all want to be the ones who discover the new thing, or who invent the new thing if it's in business, or find the new niche in a business setting. And so in science, it's definitely true. When you send in a paper and you've got a brand new idea, you're going to get even more strident criticism from your reviewers because they're going to be a little bit jealous that they didn't think of it. And that's actually a great pushback. That keeps the whole enterprise on the straight and narrow. Nobody gets away with outlandish things because of that human nature.
And I think people who aren't in the scientific community may not realize that the stronger a consensus becomes on an issue, the greater the reward to being the one person who successfully challenges and overturns what may have become conventional wisdom. That's where Nobel Prizes are won.
That's absolutely right, and it's exactly an example of the very intentional sort of provocation that I'm talking about. Exactly right, and so it's in that light, it's surprising no one's making predictions about a snowball Earth. They could; it would be provocative, but it doesn't have any cachet.
However, the Royal Astronomical Society, according to Steve Goldstein, a regular viewer, thank you, Steve, predicts a mini ice age in 2030 from sun emission patterns. So, given that prediction, what are we supposed to think? And is that just a little aberration due to sun emission patterns that's not really related to what you see happening with climate?
Well, that is a factor, of course. How much energy, the whole ball of wax starts with the sun. So that's where all the energy for our weather and climate and ocean system comes from. So there are fluctuations in that. We've had satellites measuring that since about 1979. So we have a pretty decent record now and have some sense of a periodicity in the satellite record and therefore of the solar output record. It's quite small. It's less than 1%. Doesn't have to be huge to make an impact on the global climate. The thing is, it's competing against our continued increase of carbon dioxide in the atmosphere, which is a real thermostat, turning the thermostat up. In 1957, we had about 310 parts per million. Now we just last month crossed over to 415 parts per million. We've not been to 400 parts per million. That is molecules per million molecules at random in the atmosphere, our carbon dioxide. We've not been at that level in at least 8 million years. And that is a direct consequence of industrialization because nobody guesses about how much petroleum is being used for a reserve or being put into the marketplace and being used because it's a global industry. Everybody knows exactly how to account for what's been extracted. And the extraction perfectly fits with the amount of addition of carbon dioxide. So, if the sun does dim a little bit, let's say 0.5%, which might be what the Royal Astronomical Society is talking about, and they may have some information that leads them to that conclusion, that's going to compete as a cooling mechanism against the increased carbon dioxide fraction, which makes it harder for the Earth to lose energy back out to space.
He didn't ask it, but I know Eric Johnson is thinking this. How did we know how many parts per million we had 8 million years ago?
Oh, anybody who's ever skated on a lake here in Wisconsin can understand the answer to that question. So here's what you do. Anybody who's ever skated on a lake knows that there's air bubbles in the ice. And those air bubbles have exactly the same chemical composition as the air that's currently on top of the ice and that you're breathing or that a mammoth is breathing 15,000 years ago. And so if you have ice preserved at high latitudes in the ice core, you've been drilled down. And then based on dating how far down you've gone to how old the ice is, you can tell this bubble in this ice at 30 feet down is 8,000 years old or something. You bring it into the laboratory. I don't because I'm clumsy. I couldn't do this. But chemists do. They bring it in the laboratory and they analyze the chemical composition of the air that's been trapped in that bubble for 8,000 years. And that tells them to a really good degree of approximation what the carbon dioxide or neon fraction was, the oxygen fraction, all that. So that's how we do that. Isn't that great?
That is very cool.
It's
very
awesome.
Interesting.
Yeah.
Now, what's tricky about that is, you can tell me that, and I can say, well, John's a smart guy, is an honest guy. I believe that because I know you. But unlike some other areas of, say, applied science like medicine, where we can see the obvious impact of science and knowledge in the treatment and care that we're able to deliver, say, for cancer. There's constantly new drugs being developed, and we can really see the progress in medicine, and we all experience it firsthand through friends, family, loved ones, in different forms and in different areas of medicine. We can't necessarily really see it in some of the things you're talking about because we're talking about really long-term changes in, we won't know for sure that we were right until we see what the temperatures are 40 years from now. And of course, you're saying that may be too late.
Well, here's a two-pronged answer to that. First, we can look back at correlated fields as well, sort of pollen, tree rings, things like this in the near past. In the distant past, you look at fossilized things that are not air and so on. And there's reasonable correlations between a warmer planet at a certain time would have different kinds of vegetation, a colder planet would have different ones. And so the fossil record really does trace out the very same things we find in the ice cores from Antarctica. Those are the ones we can go back far.
So you can cross-reference some of these.
Yeah, so you start to see how the things are connected, and that gives you confidence about the individual measurement of carbon dioxide fraction. So you're right. If that were the only thing you had, you got to make sure you're paying attention to other things that are going on. You don't cherry pick. In terms of the future, in terms of where we're going to go next, it's I like to think about this analogy. If you're going to have a picnic in your backyard and you got a giant wasp's nest in a tree that's kind of central to where you're having your picnic, you have a situation there. You have to decide, how will I have my normal event in the face of this looming threat? And the last thing you probably want to do is go and poke that hornet's nest. You probably don't want to try and make it worse. And so even taking an entirely conservative point of view, and I mean it in the strict small c definition of the word, you try your best to make things as unlikely to change in either direction as possible, rather than provoke further change, when experts are telling you the very things we continue to do seem to be pushing us in the wrong direction. So I think that's really the conservative approach. The true conservative approach to this issue would be to try to begin mitigating what we're doing. And I have a feeling we can spawn brand new businesses by doing that. I really do. We put people on the moon just 40 years ago. We can do almost anything there.
You've got a copy of your book that you wrote there.
Oh, yeah.
On Reginald Sutcliffe.
Right.
And, that book really does a good job of documenting a lot of the progress that's been made in our understanding of weather over the years by people who study weather and climate as you do. I mean, isn't it true we've gotten much better at predicting weather and even for further out periods? I mean, it's not perfect, of course.
No.
And, much harder in New England where, we always used to say in one day you get all 4 seasons.
It's very true. I know. There's not many places that don't say that, but there's some that really deserve that moniker. I think I lived in one, and you did too. Unbelievable. Sutcliffe was a genius, a creative genius, and that's kind of what happens with big advances in science. It's somebody picking up an old problem and just looking at it from another perspective and saying, wait a minute, how come nobody ever thought of it this way? And his real genius was to inject a dynamic physical rigor to an approach to looking at weather systems. Up till 1939, that had not been done, amazing as it is to believe. And I think that the progress that he made, he came from a lower middle class background. This was all a function of the tremendous advances that the British society made after the horrors of the initial industrial revolution. It's in the book, how they ameliorated those child labor situations and got schooling for kids and so on. And eventually the lower middle class were going to college at the university level in England. And that prepared us to beat the Nazis in World War II. Sutcliffe's advances at the forecast office made a huge impact on some of the operations themselves during the war, and then had a huge impact, even bigger impact in the decades after the war. And so we have come, I think, numerical weather prediction, that is making forecasts of the weather with computer models, is the most unheralded scientific advance of the second half of the 20th century. And he stands at the foundation of the revolution that spawned it. And you're right. We still have trouble with the forecast. My wife and I, she put together a giant party this weekend on Sunday, and we had to track the forecast all through the week. Yeah, bridal shower. And it was supposed to rain by Friday. We said it's going to rain on Sunday.
Back there? Is that why you were talking about that too?
Last year I did.
Or was it just the weather?
Last year I did. And this year, no. We just had the threat of rain. It turned out to be beautiful. So we still have trouble making even 2-day forecasts. It's not a perfect science, but it is a science. It's rigorous, and that's what makes it so exciting.
Yeah. Well, it's a great book.
Thank you.
I highly recommend it. And time for a brief commercial message. I highly recommend Hamill Family Wines. Speaking of Hamill Family Wines, located in Sonoma, where we all know many wineries, in recent years and seemingly increasingly frequently are threatened by wildfires. What can we do to prevent the wildfires that we're seeing out west with these continued hot and dry spells?
That's a good question. And I'm no forester and I'm not an ecologist, but I think what you have is a situation in which there's been a coevolution of the ecology with the traditional, or I said traditional, climatological weather that you get in the Pacific Northwest or other parts of the West. To the extent that those climatological patterns and the extremes that are allowed in the climatology now are getting more extreme, occasionally, it's not every day, but that does have an impact on the ecosystem. And I think certainly we saw last year, and we're going to see it again this year now after what happened in June. There's going to be a much more severe fire season and an earlier start to it. And that does damage to, it makes it difficult for the land to protect soil because, you don't have the vegetation sucking up water and keeping it shaded and the rest. So you end up with some threats of mudslides. That's happened up in the Cascades in Washington just from land use changes, let alone from wildfires. So, and that alters the ecosystem in substantial ways, and ways that I think it takes sometimes generations to repair or recover. And they may recover in a new way. They may come up, there may be a different kind of vegetation that takes the ascendancy in the wake of these things. And it's the unpredictability of that and the unknown about that that gets people nervous, I think, especially if you're making a living off the land, whether you're harvesting trees or grapes. You don't know how that's going to change in the medium range, 10, 20 years. And that's very frightening. And I don't know if there's too much advice that, at least I can't give. And I'm sure climate and ecologists can probably offer some advice, but certainly no certainty.
And we did seek out some soil and wildfire experts tonight, but they weren't available.
Oh, too bad.
Yeah, would have been a nice enhancement. Moving on to, and I'm not sure if you're familiar with this, but Eric Johnson did actually ask a real question, not the one I made up earlier. And he wonders if you're familiar with some of the proactive solutions like intellectual ventures, geoengineering, as a way that might, as opposed to other ways to try to delay the inevitable of climate change.
Yeah.
Are you familiar with some of the geoengineering
things,
ideas? And
yeah.
What can you shed a little light on what that refers to specifically?
Yeah, so here's an example of geoengineering, and it goes back a long ways, not necessarily for attacking the climate. In fact, Sutcliffe commented on this in the 1960s on some of the efforts that were initially brought up with respect to taming tropical cyclones. One was maybe put a thin film of oil over the water in the tropics, and that will inhibit evaporation, which would then inhibit the growth of tropical disturbances, and so maybe have fewer hurricanes if you can kind of manufacture that widespread little thin gossamer of oil on the ocean. What we're talking about now with the climate system and other things is maybe transporting aerosols up into the stratosphere where they might reside for a little bit longer, and we'd have to do that mechanically by bringing aircraft up there to maybe 20 miles above the ground and just letting a stream of aerosol leave these aircraft. And they have to be huge fleets to deal with our 6 million billion ton atmosphere. But if you could somehow get an aerosol layer up there that's an unnatural one, it might act as a little screen for the sun. So again, getting back to taking out some of the incoming solar radiation, that could certainly be a cooling agent for the planet. The problem, of course, to me is, and I'm on the National Academy of Sciences board on climate and weather, and I was not a member of the group that did this study, but it just was published this year on exactly these issues, more than just the aerosol one. And of course, I knew that they'd probably come to this conclusion when they surveyed experts. The difficulty with these proposals is that it's hard to control them. How do you manufacture, first of all, enough aerosol to have an impact? And then how do you keep it where you want it to stay? And this comes back to the arguments that Sutcliffe had as a member of the World Meteorological Organization in the 60s. You can maybe, on a smaller weather scale, maybe you can ameliorate, the hope was you could ameliorate your own weather, end a drought or something. But won't that change the conditions somewhere else in the world? And how do we deal with that?
Some kind of general equilibrium system. Right?
Exactly.
And you're adding something new, and there will be a cascade of changes that go on
Right.
around that.
Right. So other things that are a little bit more basic geoengineering might be replanting forests where they've been taken down systematically. That might suck up some carbon. So there's other, much more tenable and somewhat more controllable ways that we can attack some of these issues. But some of the far-flung, science fiction Jetsons type ideas are, I think, just a little bit unconstrained. They're difficult to imagine constraining, and then you can make a problem worse. So sort of the Rube Goldberg issue.
Yeah.
How do you keep it contained?
Yeah, right. Judy Stadler asks, and I don't know, this might be a bit challenging. I know you're not an ag specialist, you're a weather guy, but you're a guy too.
Yeah.
Maybe you can help us. What does 415 parts per million CO2 mean for Wisconsin agriculture in the next 20 years? And should farmers begin to think about planting crops that tolerate warmer temperatures and maybe less irrigation? Any thoughts on that?
Yeah, well, the first part of the question is already answered. 415 parts per million does mean we're not going to cool down on the long term until and unless that thermostat is dialed down. And so that'll take a long time. Carbon dioxide resides in the atmosphere as a gas for on the order of 10 to 100 years, actually 30 to 100 years. So it's long lasting. Water vapor, invisible water gas, is an even more compelling greenhouse gas, but it gets rained out every 8 days. So you every 9 days, the total atmospheric content of water vapor is replenished with new water vapor molecules. So every 9 days, we don't have to worry about water vapor as a greenhouse gas. As a result, it has no long-standing presence, but carbon dioxide does. So it's going to take a while for us, even if we stop doing business the way we do it now, it's going to still take a while for that to go down. Mm. So I don't know if I addressed your other question. It's related now to the one that was just asked about mitigation versus adaptation. We have to do both. There's no way that one can depend on just one or the other. We won't mitigate this problem in the next 100 years down to zero. And so we have to do a combination. So this gets to this question. I think if there is a cash crop that is more amenable to a slightly different water budget than corn. Corn is about the worst plant in the world at managing water. Most grasses are, but especially corn, really bad. So if there's a plant that manages it better, but also can fit into our economy, our ag economy, that's probably something to begin mixing in at least. I think wholesale change solutions scare the heck out of me all the time. We have that on campus. Completely divest of fossil fuels. No, let's do a gradual thing. Let's prove that we can, power 50% of the campus in a 10-year time frame on renewables. Let's do it that way. And then the same maybe with ag economics. Start mixing things in, see how they work, and then maybe you go up to scale.
Yeah, of course, I always worry if the free world completely divests of fossil fuel sources. I think I know who will own them, and I don't think we'll like that.
That's right. That's exactly right. And so there's so many ripples to all these decisions, and one has to think out as many as possible.
So, question from Sarah Shute about fire NATOs. But before we take that up, you told me something interesting today about the use of the term tornado.
Oh, yes.
It was banned for a period of time?
It was banned by edict of the national, at the time, the U.S. Weather Bureau, I think in 1870 or 1880, somewhere in the late 19th century.
Why did they ban it?
There was a debate going on between a scientist in Iowa, and I wish I remembered his name, who discovered the phenomena that we now call derecho, straight line wind damage. They were different from tornadoes, and they still are, because they're physically different things. And I won't remember his name. Anyway, he was arguing with a person who was really thinking all the damage that he was assessing was caused by tornadoes. He was certainly, the individual from Iowa was certainly correct. And he kind of drummed up support for getting rid of the word tornado in his projection of his own special interest on the weather system, on the Weather Bureau. And I don't remember the details, but the Weather Bureau took that on and said nobody can use the word tornado for fear of scaring the populace. And that wasn't pulled back until the 1940s.
And did it help prevent tornadoes?
Of course not. See, that's the thing. I mean, one almost wonders, did they really think that was going to prevent tornado damage by simply declaring them not to exist? And so, yeah, it did nothing.
I guess maybe because they couldn't forecast them very well.
And in fact,
what could you do about them, right? If
that's
you couldn't
right.
Forecast them, so
that is exactly right. And the impetus to change that policy came from a famous study in 1946. Tinker Air Force Base in Oklahoma City was struck in a 10-day period by severe storms and tornadoes that destroyed 150 planes on 2 successive events. And Captain Miller, who was an Air Force captain at the time, said, we have to understand these things better. And we still use some of Miller's rules that came from that study commissioned by the U.S. Air Force after the Tinker Air Force Base disaster. Nobody died, but equipment was lost in the millions of dollars, even in 1946 dollars. And so Miller, I'm sure, came out and said, here's what happens when these sort of severe environments and they spawn tornadoes. And don't tell me I can't call them tornadoes. Look what happened at our Air Force Base. And that was the end of that.
Wow.
Isn't that cool?
That is a fascinating story, and very revealing about terminology and people's concerns about, I guess, spreading fear and maybe wanting to contain that. So Sarah Shute does wonder if you can explain the recent fire NATO phenomenon.
Yeah.
And do we expect this to be a more frequent occurrence? What's a fire NATO?
Well, they occur every time there's a wildfire, because a wildfire is of a certain size. It sucks in a tremendous amount of air. There's a description in the Sutcliffe book of the Hamburg firestorm of 1943, which is a tragedy. Like, oh my God, unbelievable event. Gave him nightmares for the rest of his life. So these wildfires suck air in from surrounding areas, and the air is a continuous substance. And so when it gets sucked in, it has to go up. And there's tremendous updrafts, and they have a little bit of spin in them, and some of them spin off into little tornadic type vortices. And if they're in the presence of fire, then it's just like a dust devil or a steam devil, like we see sometimes on Lake Mendota in the early part of the winter. You get a windy day that when the air is cold and the steam goes up in a tornadic little storm. And these fire NATOs are just that. So they're not a new phenomenon, and they're not becoming more prevalent, except insofar as maybe the wildfires are a little bit more prevalent. But if you have a major wildfire, you are definitely, if you have enough people observing it, you're going to have fire NATOs in every single one of them, all the way back to dinosaur days.
Question from Mr. Benninger. What role has cloud seeding and chemtrails of heavy metals played in the weather? He is noting that, and I don't know, I haven't heard this, but metals were found in snow in some of the winter storms in Texas.
That's commonly the case because there's dust that's lofted in these storms, and some of the dust has metallic components in it. So it might well be just from the snow. That happens with regularity. In fact, I have a colleague who works out in the California state system, and she's really big into dust, and she loves to go to Utah in the wintertime because they have the most pristine snow crystals with what she considers the best dust in the world. I'm not really sure what that means, but anyway, there's differences in dust that gets involved in precipitation. So that might be where the metallic stuff came from in the snow. The other question was related, now I forget, Mike, what was the other part of that?
Cloud seeding.
Oh, cloud seeding, yeah. I had something to say about that. Cloud seeding, there was this great idea that seemed like it might work, that if you, and it was discovered by, what was his name? Bernard Vonnegut, the brother of Kurt Vonnegut. And he was working at GE in Rensselaer, New York.
Oh.
And so they were making, I guess they had some photographic equipment in a freezer. And so Bernie Vonnegut noticed that he by accident, knocked over a cup full of silver iodide. And it fell into the freezer, and there was just that kind of, when you open a freezer and you see that little bit of fog, it turned into crystals. And he said, maybe you can seed supercooled water droplets with silver iodide. And that was 1946 that happened by accident. And so that triggered a big industry, actually, that went on through the 1960s, both here in the United States, the Climax project in Colorado, and a big project in Israel, as it turns out. For cloud seeding, the idea was if you go up with an aircraft in a cloud that looks like it might rain, but it just can't seem to do it on its own, you seed it with some silver iodide, and maybe you'll get some raindrops to come out of it. The problem was for many of those years, 20 or so of those years, was that you just can't tell whether the cloud would have precipitated or not. So you can't conclude that what you did made it rain. But I have a colleague who's a graduate school colleague of mine. Now he's a professor at the University of Wyoming, and now we've gotten computer models of cloud processes to the extent, to the degree of certainty that Bott was able to say, it's certain that cloud seeding could produce precipitation in a cloud that would not otherwise do it. But he also said, but it could not really be expected to have commercial value. And that was recently, that was 2 or 3 years ago that study came out. So it's partly a vindication and partly a, what were you guys thinking? So it's unfortunately not really a marketable endeavor.
Interesting. So, did you mention another intervention earlier about possibly putting a film on bodies of water?
Yeah, there were people who had thought that.
What would the impact be on, the aqua creatures and marine life?
Hard to know. And that's what you'd have to balance. You'd have to sort of figure out how can you put a completely inert substance on the water, inert to the ecology of the ocean, and have it still do the inhibition of the evaporation that you need. Plus, the other thing is the scale. You're talking about, portions of the ocean that are probably 1,000 or 2,000 miles on the side of a square. You have to somehow put that film on top of that area to ensure that there'll be no development. That's an enormous industrial task.
Yeah.
And then when there's waves, aren't the waves, just like when you're doing the dishes, aren't the waves going to break up the film? And so there'll be all sorts of holes in it and so on. So they're all interesting ideas, but they're not tenable.
Or at least you would say, thus far.
Thus far, I would say they're not tenable.
Keep thinking.
Yeah, keep thinking is right. That's right. Keep thinking.
Right.
Keep hiring Wisconsin grads. They'll solve your problems for you.
So QB2, that's Alyssa Robertson. She's the backup host.
Okay.
Is chiming in with her own question. Can you talk about the connection between climate change and pandemics, and in particular, is the permafrost pandemic a real possibility?
I'm not familiar with that. Is there something that's some virus lurking in the permafrost, perhaps? Is that the idea?
Yes.
I had not thought about or heard about that, but the permafrost is disappearing in some places quite rapidly, and I can only comment on that side of it. If there is a virology side of that, that's an interesting story. I don't know about the virology side, but the permafrost is most definitely losing ground as the climate warms, because the climate in the northern hemisphere is warming faster in the highest latitudes than it is at our latitude and further south.
I guess we'll have to find a new expert to take up QB2's question in a future segment.
Yeah, that would be a great conversation.
Yeah. Well, we are bumping up on the top of the hour, John. I was wondering if you had any final thoughts you wanted to share with the audience about what we can do to monitor things, do a better job of taking care of our own role in weather and climate. What advice do you have for people?
I guess I always like to have an opportunity to say something about the endless ingenuity of this country. We live in a phenomenally exceptional country. People are free to educate themselves. We can always do better at that. People are free to express themselves. People are free to invent things. They get to take chances with businesses. They get tax breaks to take those chances. These are all good things. I think the former President Obama called that a capacity for risk. We have a huge capacity for risk in our country, both in our human resource pool as well as our wealth. And I think if we can put a good fraction of, or some fraction of our effort in both of those places toward solving this problem, trying to, first of all, there's 2 ways to solve it, or 2 steps. I think first, pull it back, and then see where we are once we halt a continued growth of fossil fuel, carbon dioxide in the atmosphere. And then take a survey once we've stopped it and see what we should do next. But we should take a sober, collaborative approach on this, and we shouldn't be afraid of the problem, because we can solve it if we put our heads together and we decide that we're each going to give something up. Various sides of the arguments. We're going to give something up, and we're all pushing in the same direction. I think that America's foes have always underestimated us, and I hope we don't underestimate ourselves.
It's a great message, and sometimes I think America hasn't had a common unifying challenge that we've been able to rise up and meet together in quite some time.
That's right.
Sometimes without that, you wonder, in a country like ours, if we can just all go about maximizing our own little part of the part of the world and not be thinking so much about the collective. And it's been a while since we've had anything
I
that's
think that's
pulled us
true.
together.
That's true. And we shouldn't be afraid of self-interest. I think that is one of the things that propels advance.
No question.
But if we can corral that, as you say, in a unified national campaign with everybody's self-interests on the table, exposed and described, we can conquer this thing.
Yeah.
So that's what I hope we can do.
Well, throwing around self-interest like that in a positive way, I want to give you an honorary economics degree. I don't confer those very often on the show, but here you go, the first one ever.
Thank you. I
And
feel great about that, Mike.
thanks for bringing the Reginald Sutcliffe book. And again, I want to thank our title sponsor for tonight's show, Hamill Family Wines, and our Hamill Faculty Fellow and Professor of Atmospheric and Oceanic Studies, John Martin. Thanks for being here tonight.
Thanks very much, Mike. And thanks to the Hamill family for the Sutcliffe work. You helped me out. Appreciate that.
Great. Well, we'll be back again in 2 weeks with another exciting segment. Could be QB2 with permafrost, but you'll have to wait and see. In the meantime, I hope everybody has a great couple weeks of summer here. We're into July, and it's a great time to be in Wisconsin, I'll tell you that. And we'll see you again in a couple weeks on Wisconsin.
You can try, but you'll never stop a badger. Because we badgers are born with curious minds and endless heart. When we see a curve in the road, we speed up. When there are mask shortages for first responders, we make our own supply chain. When there's a world on pause, we sharpen our claws. Through thunder, fire, and pandemics, we'll keep going. Because after all, you can't stop a badger.